This session will be a group discussion on Chandravakya-s in Tamil texts of astronomy. For this, I invite Professor MD Srinivas, Center for Policy Studies, Chennai, Professor R Venketeswara Pai, Department of Humanities and Social Science, IISER, Pune, then Professor V Ramanathan, Department of Chemistry and Center for Indian Knowledge Systems, IIT BHU. The discussion will be about specific usage of Katapayadi Sankhya. There are different kinds of Sankhyas used in Bharatiya Ganitam and Jyotisham. Āryabhaṭīya Sankhya is one. Bhūtasaṅkhyā, Katapayadi Sankhya, different systems that have been used. Katapayadi Sankhya uses different aksharas to represent different numbers based on vyanjanas, the consonants. Whereas we see a variation of this using swaras or vowels in a 12th or 13th century text, Tamil text on astronomy, where due to certain constraints, vowels are used to represent Chandravakya-s. This will be discussed in detail in this session. I welcome all of you and the panelists.
Thanks to IKS division and Atharva forum for organizing. This is about representing numbers. So this roughly the outline of today's presentation, a brief introduction. Then we discuss what are how numbers are represented in Indian Shastric texts, all even literary texts. There are 4 such systems that we see. Then after that we will discuss the technical details of Chandravakya-s in Indian astronomy. So first is, what are Chandravakya-s? So Vakyas are linguistic phrases. They serve as aids to our memory, mnemonics, to represent either pure numbers, or here in the case of Chandravakya, they represent the true longitude of the moon over a period of 248 days. Now moon moves in an elliptic orbit around the earth. The average period in which moon is seen to go around all the 27 nakshatras is 27.33 days. The variation of the speed of the moon depends on the distance in terms of longitude between the moon and the apogee of the orbit. So the elliptic orbit has a point which is closest to the earth, it has a point which is farthest to the earth. So that point which is closest is called apogee. So the distance of the moon from the earth in terms of the longitude, that is what determines the variation in this is Kepler's second law, that the area swept out will determine the velocity. Apogee itself is also moving. Unlike in the case of the sun, where the apogee was 78 for a very long time, it used to change by only 10 seconds or even less over a year. In the case of the moon, the apogee changes also considerably. So the successive conjunctions of the moon and the apogee happens not in 27.33 days or 32 days, it happens in 27.55 days. So the apogee has moved a little bit and the moon has to cover 0.22 days more to reach the apogee. So this period is called anomalistic month, because the distance between the moon and its apogee is called anomaly in modern astronomy. It is called Kendra in Indian astronomy. So the Chandravakya-s are Vakyas of Vararuchi, which give the longitude of the moon over a period of 248 days. That is because 248 days is roughly equal to 9 anomalistic months. 27.55 into 9, you will see is very closely 248. So in this cycle, for each day, how much the true longitude of the moon changes, that is what is Chandravakya. This will be again explained by all the speakers during the course of next 1 hour. But before we proceed, we should have some initial idea of what is Chandravakya. So the first Vakya is called Girnashreya in Sanskrit, and how it will represent a number. It represents a number 12 degrees 3 minutes. This Sanskrit phrase Girnashreya represents the number 12 degrees 3 minutes. There is second Vakya which is called Dhenava Shrihi. This Sanskrit phrase represents the number 24 degrees 9 minutes. So how it represents will be explained later. But what this means is, if someday at some time moon and the apogee are together, then exactly at the same time next day the true longitude of the moon will be 12 degrees 3 minutes plus whatever was the longitude the previous day. So if lambda was the longitude of the moon and also the apogee at some time some day, the next day at the same time the longitude of the moon will be lambda plus 12 degrees 3 minutes. The next day, second day, it will be lambda plus 24 degrees 9 minutes. So it goes to the credit of this great astronomer Vararuchi, supposed to have stayed in Kerala around 5th century. He formulated this 248 vakyas. Now, of course, before going into it, there should be something about what is Tamil text of astronomy. So I will start with a small story. In 1952, Otto Nagelbauer, who is considered a very great historian of mathematics and astronomy, he has written a 1500 page 3-volume treatise on history of ancient mathematical astronomy. He wrote a paper called Tamil Astronomy in 1952, and there he attributed this, what is called this vākya method, to a separate tradition in India, separate from what is called the Sanskrit astronomy, and this was something that is special to Tamil Nadu, and he called it Tamil Astronomy. And the evidence he took for this was a book written in 1825 by a British officer called John Warren. It was called Kala Sankalita. This officer, British officer John Warren, was the main observator in the Madras Observatory setup. So he went to Pondicherry and he met an astronomer called Swaminathan Sheshaya, and that Swaminathan Sheshaya explained how a lunar eclipse is calculated, and he calculated it in a period of half an hour to 45 minutes before John Warren. Then John Warren took up all those details and wrote it in this book Kala Sankalita, and he showed how his calculation of the eclipse was fairly accurate, midpoint and the time, all within a few minutes. After writing this article, towards the end of it, at a footnote, Nagelbauer says, now there is some more thing I have discovered. 60 years before John Warren, there was a French astronomer here called Le Gentil, who was visiting India to observe what is called the transit of Venus, which happens rarely. There was a transit of Venus across the solar disk that happened in 1769. And this transit of Venus was to be observed. So Le Gentil came to India. He stayed here a couple of years. At that time, he met another astronomer in Pondicherry. That Pondicherry was French territory. He met one ஞானமுத்து. And ஞானமுத்து again calculated for him a lunar eclipse at the end of 1768. And Le Gentil wrote a detailed memoir in French explaining how ஞானமுத்து just brought this. This was the man who brought these cowrie shells with him, and with nothing else, in about 40 minutes he calculated the lunar eclipse that was to happen in December 1768. And then Le Gentil went and compared it with the de la Hire and other tables, which were the latest tables that he had, and he found that the calculation was quite good. So this evidence was very much alive in late 18th century and early 19th century. And that this looked different. These people are just keeping cowrie shells and doing, they didn't know any Siddhantas. So they thought this is separate, and they even theorized that there was somewhat of a fight between the Brahmins in Pondicherry and these Tamil astronomers. The Brahmins kept their Siddhantas secret, and so all this is written by Le Gentil also. Nagelbauer hints the same thing also. And of course, soon enough, in about 15-20 years, it was all proved to be wrong, because this Vākya system of astronomy was widely known in South India, Kerala, Tamil Nadu and Andhra Pradesh, Karnataka. So we will see how this is a tradition of Tamil tradition of astronomy, but this is not the Tamil tradition in the way Nagelbauer or Pingree or others wanted to see, or Indologists wanted to see. It's a Tamil tradition which is in close contact with the Sanskrit tradition, and they are both mutually complementing and adding to each other in the progress of this great tradition of astronomy. Now we come to the first part of the talk, representation of numbers. We should know India was a pioneer in representing sounds. So we discovered letters after analyzing the phonetic properties of the sounds. What is the region in which the sound emanates, that is called the asya, and what is the effort that is made, that is called the prayatna. So these two things, based on this, all vowels and consonants are characterized, and that varnamala that you see, ka, kha, ga, ga, nga, cha, cha, ja, ja, nya, etc., that's all a sub part of this. This was all perfected at the time of Pratishakyas, about 400-500 years prior to Panini. This varnamala was finalized, and each sound was vowels, and the position of their articulation, kanthya, talavya, the throat, the guttural, the murdhanya, cerebral, dantya, the teeth, osthya, and similarly what are all the sparsha, the what is called the harsh consonants, then ghosha, the voiced one, unvoiced one, mahaprana, aspirated consonants, all this is classified. And the script that Indians discovered, the Brahmi script, was uniquely representing the sounds, and this spread not only all over India. There is a southern Indian Brahmi also, which goes back to 4th or 5th century before the Common Era. This spread to the whole of Southeast Asia, and in fact Dalrymple explains in several videos recently how the Southeast Asian scripts originated from the South Indian scripts, and it went also to Korea, and very large part, and the Latin and Cyrillic, those scripts were based upon Semitic origin. They had this arbitrary ordering called A, B, C, D, etc., alpha, beta, gamma, etc., which had nothing to do with the sounds of those sounds that these letters represented, whereas this was a very scientific one. Similarly, we discovered the decimal place value system also. It is these two discoveries. Decimal place value system made all arithmetic calculation child's play, and it was this which made Indians have a universal literacy and numeracy achieved almost %, all through its history from about 5th century, 4th century onwards. So this place value system, everybody knows what it is, and it was discovered from the Vedic times, where the decimal way of talking about numbers, decimal way of nomenclature of numbers, and then we started with the rough idea of zero philosophically in Panini's Ashtadhyayi, in the Shunya of the Buddhists, and in the Abhava of the Nayayikas. So by the time of Pingala, the zero symbol had come, and the full mathematics or arithmetical calculation and algorithms, including square roots and cube roots, of using the place value system, decimal place value system, you find it in Āryabhaṭīya, and the complete theory with negative numbers and also the arithmetic of zero is there in Brahmagupta. This is what was adopted by the whole world as the algorithmic way of calculation. This is very good. We have very beautiful symbols from which we can calculate 10 digits, 1, 2, 3, 4 to 9 and 0. All our scientific texts were written in poetry, and there were also sutras. So how do you refer to number? So if you read Līlavati, he cannot be saying Shashtyabda, Chaturthi and all that. So it makes the poetry very complicated. So you need various ways of introducing numbers in poetry, in sutras, and various systems of using numbers by phrases of the language. Now, oldest system was what was called Bhūtasaṅkhyā. That is, you use the fact that in common parlance, I means 2, Veda means 4, Vasu means 8, if anybody who knows Sanskrit tradition. So you all, Guna means 3, Ritu means 6 in India, not 4. And so all this will be used to denote numbers. This was called the Bhūtasaṅkhyā system, which was used heavily both in Sanskrit and all Indian languages. Then there were other systems also which used linguistic phrases. So those systems we will discuss briefly to start with. So Bhūtasaṅkhyā system is there even in some of the Kalpa Sutras and things like that, where they use the word called Gayatri. Gayatri is a Vedic Chandas, where the total number of syllables is 24. So to denote 24, they will say Gayatri. In the Kalpa Sutra is the Shrauta Sutra, Griya Sutras, etc. Similarly, they will use the Brihati, that will denote 48. There are 48 syllables in the Brihati Chandas. Similarly, even things like Kha, the number of stars, 27, this is all used. In Vedanga Jyotisha, which is also 1200 BCE, there are Rupa and Kha used, 27 Bha is used for 27 nakshatra, Rupa is used for 1. But later on, by around the turn of Common Era, this Bhūtasaṅkhyā got combined with the decimal place value system that we had. And amongst the texts that are available where the Bhūtasaṅkhyā together with decimal place value system is used, we have the Varahamihira's Panchasiddhantika. It's used in Brihajataka also. So in Varahamihira's Panchasiddhantika, second chapter deals with what is called Vasishta Siddhanta. The second verse goes like this: Rasaguna Navendu Yukte, Shashiguna Khagунodhrite, Ghana Yugane, Sheshe Navabhirgunite, Gatayo Ashtajidaihi Padam Shesham. So here the number 1936 is represented by Rasa Guna Nava Indu. Rasa is Shadrasa 6, Guna is 3 gunas 3, Nava is just 9, Indu is the moon only 1. Now you have to write these 4 numbers, but you have to write them in the reverse order. Why do you want to write it in the reverse order? Because in the reverse order you know the actual place value. The last number is the first the 0th order digit, then 10th order digit, then the 100th order digit. So you therefore write it from right to left, the number, though you read it from left to right. And so this Rasaguna Navendu, Shashiguna Khaguna. Shashi moon 1, Guna is 3, Kha is 0, Guna is 3. So this represents the number 3031. So this 3031, and finally Ashtajina, that is 8, Jina are the Tirthankaras 24, that is 8, and then to its left you write 24, 248. These 3031 and 248 are the most important numbers for today's talk. So they first occur in Varahamihira's Panchasiddhantika, in Vasishta Siddhanta, in the computation of. Similarly, for calculating pi, Nilakanta has quoted a verse of Madhava which uses Bhūtasaṅkhyā. So here Vibhuda, it is the number of Devas 33, Netra is 2, Gaja, the Ashtadigajas 8, Hutashana, the number of sacrificial fires is 3, Hahi, the number of serpents is Ashtasarpa 8, 3 is 3, Guna is 3, Veda is 4, Bha means nakshatras 27, Varana is again Gaja, Ashtagaja 8, Bahavaha is arms 2. So this number 2827433 88233 is the circumference of a circle whose diameter is Nava Nikharva, 9 into 10 to the power 11. So if you calculate this ratio, circumference to diameter, it gives the value of pi accurate to 11 decimal places. This is the verse of Madhava quoted by Nilakanta Somayaji in his Āryabhaṭīya vākya. So this is the Bhūtasaṅkhyā. It's used extensively in mathematics, in all other shastras, not only in Sanskrit, in all other subjects. The next thing is called the Āryabhaṭīya system of numeration, because it is used in the text Āryabhaṭīya of Āryabhaṭa, perhaps written around 499 of the Common Era. So Āryabhaṭīya system of numeration is the first one which uses syllables, aksharas to denote numbers. So here the consonants are all given numbers, ka, kha, ga, gha, nga, cha, cha, ja, jha, nya, are given numbers 1 to 10. Ta, tha, da, dha, na, ta, tha, da, dha, na are given numbers 11 to 20. Pa, pha, ba, bha, ma are given 21 to 25. Ya, ra, la, va, sha, sha, sa, ha denote 30, 40, 50, 60, 70, 80, 90, 100. And the vowels determine the position, but position at even place values. So akar and akar, both dirgha and hrasva, denote the unit place value. Ikara and ikar will denote the 100th shatasthana. And similarly u, r, r, then a, o, I, au. So they all denote even place values. This Āryabhaṭa explains just in one verse in the beginning of Dashagitika. Then in doing this first verse, Āryabhaṭa uses Yugaravi Bhaganaha Kyugr. So here the number Kyugr occurs. That's one word number which I will explain, and then we will move on. Q, Kha and Ya. Kha is 2, Ya is 30. So Q is 32, and it has a Ukara associated with it, that is 10 to the power 4. Then you have Gr. Gha is 4 and Gr is 10 to the power 6. So Q is 32 into 10 to the power 4. Gr is 4 into 10 to the power 6. So Q Gr is denoting 43,20,000. So basic problem is, you will see for the moon Chayagigishu, Chayagigishu Chilr, that is 5775336. So its pronunciation is difficult, it doesn't make the good poetry, but it's highly compressed, almost like Panini's sutras. So this was Āryabhaṭīya system. It was used only in Āryabhaṭīya, but he had given this principle that you can use syllables for numbers, and that gave rise to the next system called the Katapayadi system.
Namaste. The Katapayadi system is also similar to Āryabhaṭan system, where it's also an alpha numeral system where the consonants are used. So in Bhūtasaṅkhyā system we have seen that the numbers are expressed and they are meaningful phrases or sentences, but in Āryabhaṭan system it is precise but they are not meaningful. So both the positive aspects of Bhūtasaṅkhyā and Āryabhaṭan system will be taken care in Katapayadi system, because when we express a number, an arbitrary number, using Katapayadi system of numeration, it will be both meaningful phrase as well as it will be precise, or it will be more shorter as compared to Bhūtasaṅkhyā system. Both the Katapayadi also use consonants to represent numbers. Unlike in the case of Āryabhaṭan system, the vowels do not have numerical significance, and in Āryabhaṭan system the consonants K to Ma were representing numbers from 1 to 3 up to 25. But in the case of Katapayadi, in the name itself, the Katapaya, the numbers between Ka and Ta is 10. So Ka, Kha, Ga, Gha, Nga, Cha, Cha, Ja, Ja, Nya, they represent number 1, 2, 3 up to 0. Then again, starting from Ta, Adi means starting from or etc. Kadi, Tadi, Padi and Yadi. Ka etc. represent number 1 to 0. Ta etc. again represent number 1 to 0 up to Na. Then Pa, Pa, Ba, Ba, Ma, again 1, 2, 3, 4, 5. Then Uyirêḻuttu, Sha, Sha, Sa, Ha, number 1, 2, 3, 4, 5, 6, 7, 8, and another letter L, which is found in Vedic literature, also in some of the South Indian languages, that is L, it represents number 9. So now let us see how this system works with an example. Let us take the phrase Dehali. First, what we need to do is we have to split this into different subunits. So when I say subunit, it should contain at least one vowel and at most one vowel. Okay, at least and at most one vowel. So when we will split this into subunits, we will have 3 subunits as far as the phrase Dehali is concerned. So now Dehali. So now the number corresponds to corresponds to the consonant the itself, because vowels do not have numerical significance. So that is the beauty of Katapayadi, where it is Ka or Ka or Ki or Ki, all these represent number 1. So we have number of freedom, or we have to choose and form a meaningful phrase. So the number the subunit there corresponds to number 8, and again Ha corresponds to number 8, and Li, Yara, La, that is 3. So they 8, Ha 8, and Li is 3, and we have to reverse the order that we have done in the case of Bhūtasaṅkhyā, that represent 388 for Dehali. So now let us take another example, which is Dilli, which is slightly different from here. The difference that we can observe is there are 2 consonants. There is a conjoined consonants in Li. In this case, when we split this into 2 subunits, we have the first subunit is Di, which represents number 8, and we have second subunit which is Li, which contains 2 consonants. So in this case, we need to consider that particular consonant which is proximate to the vowel. In this case both are same, but we need to consider only one consonant, that is La, and the number corresponds to La is 3. And again, if we reverse the order, we have number 38. Now let us take another example, Indraprastha. In this case, we have a vowel which is standalone. Though vowel associated with the consonants do not have numerical significance, the standalone vowel represents number 0. So, E in Indraprastha represents number 0, Ndra, again there are 3 consonants, conjoined consonants, Na, Da and Ra. We need to consider only Ra, which represents 2, then Pra again 2, Stha we have to take Tha, that is 7, and if we reverse the order we have number 7720, that is number corresponds to Indraprastha. So, now the Katapayadi system, as Professor MD Srinivas has mentioned, it dates back to 5th century. This is used in representing Chandravakya-s. Chandravakya-s, the Chandravakya-s that we see here is Girnashreyaha, Dhenavashrihi, Rudrastu Namyaha, etc. They are known as Girnashreyadi Vakyas because it starts with the phrase Girnashreyaha. It has something to do with moon's motion, then hence it is known as Chandravakya-s, and it is composed by Vararuchi, so hence it is also known as Vararuchi Chandravakya-s or simply Vararuchi Vakyas. So, now they are 248 in number, and each Vakya represents the true longitude of the moon on each day, which means the Girnashreyaha is the true longitude of the first day when the anomaly of the moon becomes 0. We have to start counting from when anomaly becomes 0. Anomaly is Kendra, or the longitude of moon minus longitude of its apogee. So, that is the first Vakya. The second Vakya represents the true longitude of the moon on second day. Similarly, 248th Vakya Bhavet Sukham represents the true longitude of the moon on 248th day. When I say true longitude, it is nothing but the angular position of the moon from a fixed star, which is called Ashwini Nakshatra or starting of the Mesha Rashi, Meshadi. So, now how do we understand that the number corresponds to Girnashreyaha is 1203. When we use Katapayadi, when we apply Katapayadi system here, since this is expressed using Katapayadi system of numeration, we have Ga, Gi is Ga, that is 3, then Na is 0, Sh, Shra, we have to take Ra, that is 2, then Ya, that is 1. So, and if we reverse the order, we have 1203. But unlike in the case of Indraprastha or Delhi, here we have 3 subunits, like these has to be divided into 2 syllables, and each 2 syllables represent 1 unit. The first 2 syllables, that is 00 in Girnashreyaha, represents Rashis. One Rashi is one zodiac sign which represents 30 degrees. Second unit is in degrees, that is 12 degrees, and 03 is in minutes. So, the true longitude of the moon on first day using the Vakya Girnashreyaha is 0 Rashis, 12 degrees and 03 minutes. So, which means moon is in the first Rashi, 12th degree, and the minute part is 3. So, when we look at, so since there is an absence of 2 syllables, we need to consider it as 00. When we come to that 124th Vakya, we have Ramagiyate, where you have 5 syllables. The first Ra is 2, then Ma is 5, then Gi is 3, Ya is 1, then Ta is 6, Ta in Te is 6, then there is an absence of syllable, so that is to be considered as 0. So, now if you reverse the order, we have 0, 6, 13, 52, that represents 6 Rashis, 13 degrees and 52 minutes, which is the true longitude of the moon on 124th day from the time of conjunction of moon and its apogee happen at the sunrise.
Both Bhūtasaṅkhyā and Katapayadi, through which we saw how the positions of the moon was calculated or was known. And as Professor MD has told you in the beginning about how Indians were adept in understanding sound and representing them, and hence the Sanskrit Varnamala, and from there Katapayadi representation of the true longitudes of the moon via Katapayadi system. All that sounds good, but the moment you switch from Sanskrit to say Tamil, and not the Grantha Tamil which was used to write the Sanskrit, but the non-Grantha Tamil, the Tamil that was widely known or is being widely practiced even now, we see an apparent problem. Problem in the sense, you can see that in the Sanskrit Varnamala, it is from Ka to Ma, that is Amogha sparsha, ghosha, all those things that you saw. The Tamil thing, even though there are sounds for corresponding to some of them, the lexical representations of them are not present, especially of this central three, that is the Mahaprana of the guttural kha, then Mahaprana of the other series cha, tha, tha, pha, and the other gutturals which are the ghosha sound, that ga, ja, da, da, ba, and gha, jha, da, da, ba, the Mahaprana counterparts, are missing from the Tamil lexical system. That's why it starts from ka, and a Panchama Vyanjana, it comes the nasal ka, nga, cha, nya, ta, na, ta, na, pa, ma, ya, ra, la, va, ya, la, ra, na. That's how the Tamil Varnamala goes. So if we want to now represent using Kaṭapayādi, there seems to be an apparent problem in this case because of the lack of these vital letters which are useful. So as a consequence, the Tamil astronomers who were closely following perhaps the their Sanskrit predecessors, simultaneously came up with another ingenious way to represent numbers similar to Kaṭapayādi, but not exactly using the consonants that the Kaṭapayādi relies on. What is this Tamil ingenious way? You get rid of the consonants. You concentrate only on the vowel part. Quite opposite to what the Kaṭapayādi was, because as Dr. Pai said, if you had ka, ka, ki, ki, ku, ku, ke, kai, everything would represent the number 1, because the vowel associated with ka is of not consequence. Quite opposite is in this case, because whether it is ka or kha or ga or ma or pa, it doesn't matter, because all these consonants are associated with the vowel only harsva akara. That harsva akara will get the numerical significance. So all the vowels are what are given the numbers. So a harsva is 1, a is dirgha, which gives the number 2. Similarly, e, u, and then you have in the ekara, you have 3 different variations, a and I. Whereas Sanskrit has got only a and I, there is a harsva and a dirgha a in Tamil and other South Indian languages also. And so is the case with respect to O. O, harsva, ho, dirgha and au. So numbers 1 to 9 are mapped for these vowels from a to I, and O and O, harsva O, dirgha O as well as au are mapped to the number 0. One caveat, even though the au is mapped to 0, but in the texts that we have looked upon, there is no any instance of occurrence of au in it, but just for the sake of completion of the mapping, it is we are proposing that this au also, if it is mapped to 0, it is without any loss in generality. So what is the numeration scheme here? These vowels are going to dictate what the number is going to be and not the consonant to which these vowels are associated. Rest of the thing remains the same, that is, you have to read the numbers from the right to left in order to get the exact number that is being denoted by the lingual. So if we are talking about the numeration scheme here, where I would like to differentiate between another representation of numbers that is in vogue in the Tamil literature, which is what is used just like a Roman numeral, like how you have X for 10, V for 5. They are mere representations, but they are not like a numeration scheme. Such kind of a representational practice has been in vogue, which is which it appears like a Tamil consonant. Some of them, like the ka, is used for representing the number 1. Similarly, what appears as a letter u in a truncated way appears like it used to represent the number 2. And the Panchama Vyanjana of the guttural, that is ka, nga, a truncated version of it is for number 3. A slightly modified version of the letter sa or sha represents 4, ru for 5, so on and so forth. It's for until 9, and then they have separate, then there are multiples of it. Suppose I want to represent the number 11, it will be ka, ka. And similarly, the number 12, if I want to represent, it is just ka, u. So it's a representation. which is very different from the numeration scheme that is being talked about with this mapping. And just to illustrate it with an example, suppose you take the word parahitam. There are apparently four consonants. With three of them you have the vowel associated with it, four of them vowel associated with it, and the fifth one, which is im, you have no vowel associated with it. So pa is ip plus a, similarly ra is ir plus a, he is h plus e, and ta is it plus a, to which you have the numbers 1 1 3 1, and you reverse it and you get the number 1 3 1 1. Similarly, you take another word uڵḷamuḍaiyān. So you can have u, which is a number 5, then la for number 1. Similarly, if you see, this will represent the number, once you read it, reverse it, 29,515. Now it so happens that in this text, Cūḍāmaṇi Uڵḷamuḍaiyān, which happens to be a Tamil text, and as Professor MD has gave it in the introduction part, this is either roughly a 13th century or a 14th century text, where we come across for the first time the numbers represented using linguistic phrases in the astronomical context. That text is called Cūḍāmaṇi Uڵḷamuḍaiyān, and then there are this has been widely studied. It has also been influential because there are later texts also which have borrowed or taken inspiration from this text. All of them consistently use this numeration scheme, which is very different from the Bhūtasaṅkhyā, Āryabhaṭīya or Katapayadi, and that's where we call this as uyirêḻuttu, which is a term for vowel or svara sounds in the Tamil language. So it's a vowel based numeration scheme that we are talking about.
So now we go to the use of this scheme in the Tamil astronomical text. So first, Siddhantic and Vākya systems, how do they differ? Professor Shriram explained in the morning. In the Siddhantic system, for calculating the positions of sun, moon and planets any day, you first find out how many days have elapsed since the time of epoch. So that is called ahargana. You find out the mean position of the planet by the rate given in the text. It gives either the number of revolutions in a yuga or something like that, and you calculate. After that, you apply various corrections, and those corrections are called samskaras. So for sun and moon in all older text, there is one correction only, what is called the manda samskara, called equation of center in today's astronomy. The planets have two samskaras, one is called manda samskara and is called shigra samskara. So these samskaras use actually in outside of India in the various earlier systems of astronomy, they were using geometrical models and linking angles with chords and things like that. In India, we were actually using trigonometric functions right from Āryabhaṭa's time, but these trigonometric functions were not functions of angles, they were functions of arcs. Arcs, circle is taken as 360 degrees and arcs will be sub part of it, and using functions of arcs, half arc as a function of half chord as a function of double the arc, that was taken as the jya function, that is a sine function. So this is how Siddhanta. But in Vākya system, all this complication is avoided. You need to calculate the ahargana, then it will tell you some quantities called khanda etc., which are quantities to be subtracted from the ahargana. Then it will tell you some other arithmetic operations using various vakyas as to how to go about to calculate the final longitudes. In that various things like khanda, dhruva, parivritti etc. come. All of them actually depend upon the nature of the motion of the celestial bodies, their rates, their apses, their perigees, apogees and their nodes etc. Now anomalistic cycle of the moon, I had already said it in the beginning, 27.321662 days is the period in which moon goes around the stars, but the mean anomalistic period is 27.554550. So the anomaly itself moves, actually if you want to know the rate of motion of the anomaly, that is something like 3232 days or 8.8 years. So if you consider 9 anomalistic months, or 110 anomalistic months or 449 anomalistic months, you get very close to integral values of days. 9 into 27.554050 is 247.9095. So it is roughly 248 days. 110 into the anomalistic month is 3031.0005. So it is roughly 3011 days. Similarly, 449 anomalistic months is 12372 days. So they become very close to integral number of days. These are called anomalistic cycles. So they come out very useful in the computation of moon. So before that, we should quickly see how from the Siddhantic astronomy Vararuchi's Chandravakya-s are computed. So in Siddhantic astronomy, because Vakya system is only a shortcut method for doing the Siddhantic calculation. So once we understand that, so now that was also emphasized in the morning talk by Professor Shri. So we first compute the Ahargana, which is the number of days elapsed from the epoch usually taken as the beginning of Kali Yuga, that is February 18, 3102 BCE, to the beginning of the given day, say perhaps at the sunrise. Now all that you need to do is to find out the mean longitude of the moon. The daily motion of the moon can be calculated. I have already said to cover 360 degrees, moon is taking 27.32 etc. days, and therefore in each day moon is travelling on the average 13.1764 degrees or 13 degrees 10 minutes 35 seconds. This is the mean daily motion of the moon. So if theta is the actual sort of longitude of the moon, it is the mean longitude minus a correction, and this correction is given by sine inverse of 7 by 80 into sine into mean longitude minus the longitude of the apogee. Theta c is the longitude of the apogee, which is also varying. Theta naught is the mean longitude of moon, which is also varying. 7 by 80 is related to the epicycle or eccentricity of the elliptical orbit. So the true longitude in Siddhantic astronomy is given by that formula. So now what is the ingeniousness of Vararuchi? Ingeniousness of Vararuchi consists in that he knows the rate of motion of theta naught minus theta c. Theta naught minus theta c is the anomaly that completes 9 revolutions in 248 days. Therefore 9 into 360 degrees are covered in 248 days. Therefore rate of motion of anomaly per day is 9 into 360 divided by 248. So after m number of days, the anomaly becomes 9 into 360 by 248 into m. So you can straight away calculate for each day what is the true longitude. So for day 1, put m is equal to 1 in that formula, at the last formula, you will get the first Vararuchi Vakya, the longitude represented by Girna Shreya. Or if you want to have more accuracy, Madhava came up with Shreya, Shilam Rajya Shriye, up to the seconds he can calculate. So the 248 Vararuchi Vakyas are calculated. Now how does the Vakya system develop? So 9 anomalistic months is 248 was something that was known to ancient astronomers. It comes in some of the Babylonian tables prior to the common era, but there is no Vakya there. There are no formulas there. There are just tables of moon's longitudes for 248 days. Both Babylonian and what are called the Greek papyri of the Hellenistic period in the 1st, 2nd, 3rd century of the common era. So this is what Neugebauer said, and in fact before him Schnabel, another sort of Assyriologist or Babylonian specialist, had written in 1924 itself that this 248 occurs in Panchasiddhantika also and later Indian astronomy. This must have been borrowed from Babylon etc. was one of the theories that was put forward. Now Varahanira's Panchasiddhantika gives Vasishtha Siddhanta, which uses this 248 and 3031, the two numbers which are anomalistic cycles, but it does not again use the Vakyas. It does not, but it gives a way of calculating the true longitude every day. And there is a certain approximation to the sine function that is done in Vasishtha Siddhanta. If the sine goes like a wave, instead of having a wave, you just think of a wedge going up and down and going down and up. So this sort of per day constant rate of change of the function was what was used as an approximation to sine. Now Chandravakya-s of Vararuchi using the full sine function are perhaps given around 500. This is what is generally dated. But afterwards in the available Sanskrit text there was a huge gap. The next text which uses vakyas, though Katapayadi is known by 500, Katapayadi is used in Sanskrit text called Parahita system in 683 by Haridatta. The Chandravakya-s alone were the only things known. There was nothing more known about Vakya system till about 13th century end, when a text called Vakya has been written. But this Vakya is a text that was actually written in Tamil region. It talks of Kanchipuram and it was written around 1282 or between 1282 to 1306. We will soon see why it is so. It has also a commentary in Sanskrit by a Tamil astronomer called Sundar Raja, who was also staying in Kanchipuram. He had in fact correspondence with Nilakanta Somyaji around 1500, and he says Nilakanta Somyaji wrote a book for me called Sundara Raja Prashnottara. So this Vakya system in its full glory appears in Tamil Nadu in 1300. So what is this Vakya method for calculating the longitude? So this is the procedure whose numerical example Professor Pai will demonstrate you soon. You take the Ahargana and subtract one number called Khanda. So in Vakya the Khanda used is 16,984, and that Khanda corresponds to a day in 1282 of the Common Era. From the beginning of Kali Yuga, if 16,984 days elapse, you come to 1282 CE. The Khanda is so chosen that on the day of Khanda, moon and the apogee are together at sunrise, and that day is close to the day you are dealing with. So Vakya should have been written in the decades immediately after 1282. Then what do you do? Whatever remains, you first divide by 12,372, note down the quotient and remainder. So you first divide by 12,372, keep the quotient, take the remainder, divide it by 3031, and take the next remainder, divide it by 248. Finally you will have a number less than 248 as the remainder. That will be the number of vakyas that you have to use. And then the text gives you three numbers, again longitudes, d0, d1, d2, d3, and you calculate d0 plus q1 d1 plus q2 d2 plus q3 d3 plus the number denoted by the vakya corresponding to the integer r3. So it is purely arithmetical operation. You have to know the three dhruvas. In a moment we will see what these three dhruvas mean. Next one. So what are these three dhruvas? D0 will tell you what was the exact position of the moon on the Khanda day, 16,984 day, which you have subtracted from your Ahargana. That was the longitude of the moon. D1 will tell you how much the longitude of the moon has changed in 12,372 days. Similarly, D2 will tell you how much the longitude of the moon has changed in 3031 days. In D3 will tell you how much the longitude of the moon changes in 248 days. These are fixed numbers which can be calculated. In fact, that last Vakya Bhavet Sukham represents 27 degrees 44, which is that D3 there. So it was this arithmetical operation that was used with these crucial divisors 248, 3031, and that was the Vakya method. This is not a complete Vakya method, it also gave a correction for this, because 248 days I said exactly corresponds to 9 anomalistic cycles. That is not true. There was a few decimal numbers missing. So the apogee and the moon do not exactly come together after 248. Similarly, 3031 days I said is 110 anomalistic cycles. There is still a small difference between apogee and the moon. So you have to make a correction. That is also given in Vakya. Now we go to Cūḍāmaṇi Uḻḷamuḍaiyān. Cūḍāmaṇi Uḻḷamuḍaiyān in the text itself says it was written in 1100 Shaka, which means 1178. But it is the first book where you have this kind of method of calculating the longitude of the moon by Vakya method discussed. But it says this book has 450 verses, 10 chapters. The 8th and 9th chapters are mathematical astronomy. First to 8th chapters are the other skandhas of Jyotisha. So the 8th chapter is called Parahita Ganitam. That is where the system of numeration that Professor Ramanathan discussed appears. So it gives a khanda called Mannan Veed Shul Kulam, and you calculate it using the way he has given, that will turn out to be 15,65,411. So that is the khanda that this book is giving. So the Cūḍāmaṇi Uڵḷamuḍaiyān in the 8th chapter is the first available book to us which is discussing the way of calculating the longitude of the moon. It starts with the same way: calculate the ahargana for the desired day, subtract 15,65,411, that corresponds to Mannan Veed Shul Kulam. Ma is 1, Na is 1, V it is Ikara, it is 4, like that you can immediately see that number comes. After that it uses two divisors, 3031, 248. We saw them just before in Vakya Karana. So 3031 is called Palliyoni and 248 is called Erirma, and then finally it again goes back, it gives a dhruva corresponding to the khanda 15,65,411. It gives the same dhruvas which was given in the later book Vakya Karana for 3031 and 248. So this calculation which later appeared in Vakya Karana, why Vakya Karana is later? It uses 16,900,000 odd days as the khanda, which is 1282, whereas Cūḍāmaṇi Uڵḷamuḍaiyān, the Tamil text, is using the khanda 15,65,411, which corresponds to 1185. So 1185 might be the date on which this calculation of moon's longitude might have been discovered, but the text itself uses another khanda for planetary motion, which corresponds to 1245. So the text can be latest, it can be around 1245, 1250, meaning that would be after that it would be written, but it is prior to Vakya Karana, and it is very remarkable that a Tamil text is giving the same method of computing the moon that was later on in a more sophisticated way given in Vakya Karana, but it is also saying we are discussing what was given in Vadamoli, given the astronomy given in Vadamoli, we are representing it in 10 Tamil for the understanding of all. So we have not come across what that book would be, but that is the importance of this text. But the continuous development of this Vakya system in Tamil tradition is borne out by this text.
The procedure outlined above by means of an example. So the example chosen here is 28th February 2025. Our aim is to find the true longitude of the moon on 28th February 2025. So what we need is the ahargana. So you can see in the picture, you can see there is an epoch which is the Kali beginning, and you can see this desired day. Desired day is 28th February 2025, on which we need to find the true longitude of the moon using Vakya method. So the number of civil days between epoch and desired day is known as ahargana, and we need to know what is known as khanda. So khanda, again once again I am repeating, khanda literally means a part of ahargana, but it is chosen in such a way that it should be contemporary as well as the moon's anomaly should be 0 at the sunrise. Ideally it should be 0 at the sunrise, but it may not occur at the sunrise. There might be finite time difference between the instant of sunrise and instant of conjunction of apogee and its moon. So now khanda we get it from the text. Vakya Karana text gives Vededa Jnana Tushtaha, which represents 16,984,000, and ahargana for 28th February, that is Magha Amavasya Shaka 1947, is 18,72,069. We need to find the khanda shesha. Khanda shesha is the difference between ahargana and khanda. Khanda has to be subtracted from ahargana, so that becomes 2,71,285. That is the first step. Then this khanda shesha 2,71,285 has to be divided by 12,372, which is one of the divisors given in the text itself, which is nothing but the moon takes these many number of anomalistic revolutions, integral number of anomalistic revolutions in 12,372. Ideally it should come back to the sunrise time, but it may not happen. There will be again finite difference between the time of sunrise and the instant of conjunction. The quotient that we obtain here is 21, and the remainder by this division is 11,473. Now we need to take this remainder, first remainder, and divide it by 3031, that is the second divisor. Quotient what we get is 3, and the remainder what we get is, that is R2 through 2380. Now this 2380 has to be divided by 248, Q3 that is third quotient, that is 9, and third remainder, that is 148, and is obviously the remainder R3 will be lesser than 248. So now we have to store the values of Q1, Q2, Q3 and R3, and first we need to find the net or resultant dhruva of the moon, that is nothing but the true longitude of the moon to be obtained, net resultant longitude from the dhruva, that is d0 plus d1 should be multiplied by the quotient q1, d2 to be multiplied by quotient q2, d3 to be multiplied with quotient q3, and we have to find the sum of all these values. D0 is from the text itself we can get, d1, d2, d3 also, this is the Senanari-nathanam, Nityadeva Sukhadhinam, Yajnayogasu Nayakam, Tanur Vishwa Sukham. These are the dhruvas, that is the longitudes corresponding to d0, that is for the khanda, then for the days 12, 372, 3031 and 248 respectively. So that is converted in third column previous. Those values are represented in degrees for our ease, for computational ease. So and the earlier obtained values are stored as q1 is 21, q2 is 3 and q3 is 9, and when we substitute these values, what we obtain is finally d net or the resultant dhruva as 168.026 degrees, and we have 148, the third remainder R3 is remaining 148, that is the vākya, the number of vākya, and the number of vākya corresponds to, this is from Chandravakya or Vararuchi's Chandravakya, Sampratam Ravihi, which corresponds to the number or the longitude 4 rashis 26 degrees 27 minutes, which is nothing but 146.450 degrees, that has to be added to the net dhruva or the resultant dhruva. We get 314.4761 degrees as the true longitude of the moon for 28th February. This from ephemeris, if we see the value of true longitude of the moon on that day, it is nothing but the 314.999 degrees, it is very closer. So even now the Vakyakarana method working fine, though there is, it is not precise, it's closer to the value of ephemeris value. So now this is just we have applied Vakyakarana method, but there are several corrections are mentioned in Vakyakarana, then Karana Paddhati, then there is another Vakyakarana by Parameshwara from Kerala school, this is known as Dhruva Samskara. Dhruva Samskara is the correction is applied to the dhruvas. Why do we need to apply the corrections to the dhruva? Because all these assumptions, all these computations have been made by assuming that khanda exactly the moon's anomaly is 0 exactly at the sunrise. Khanda is chosen in such a way that assuming that moon's anomaly is 0 at the sunrise, but actually it is not true. There is a finite difference between khanda instant of conjunction of moon and its apogee and the instant of the sunrise. So this finite time difference will add an error in dhruva, and when we multiply these with quotients again in 12372, it is again as Professor Srinivas has shown the actual values of the true longitude of the moon for 12372 days. It is not exactly, it is not a complete integral, that there is a fractional part which is there, it is plus or minus it is to a nearest integer, plus delta value plus or minus to the nearest integer. We are approximating it as 12372. That delta is due to because at the sunrise anomaly is not 0 exactly at the time of sunrise. So again those time the time difference between the instant of conjunction and instant of sunrise will add and the error will be accumulated. In order to address that, there is a samskara which is mentioned in the text itself, that is known as dhruva samskara. which will take care of this samskara, and there are other samskaras are also mentioned. When we apply all those samskara, it may come more closer to the actual value of true longitude. Thank you.
Just to put it in all in perspective, what has been discussed till now, because the theme is Tamil astronomy, and on the Chandravakya-s of that we find in the Tamil astronomy. Just to remind you, get the summary. 4 important things. Why are we harping on all these things? Because today we can compute or we can obtain the positions or the longitudes of different planets from the ephemeris. And to get into all that, just now Dr. Pai showed you what are all the necessary ingredients, which are nothing but 4 in number and very simple arithmetic. That is ahargana, and you need the khanda. And within that khanda, again, in the Chandravakya system that he talked about from the Sanskrit text, you have the 3 numbers 1, 2, 3, 7, 2. Of course, before that you had the ahargana which has to be taken, and then you had this 3031 and you had this 248. And the arithmetic that got enshrined within it. Because today, if you have to online generate a horoscope which has got to do with the positions of planets, that is the ephemeris values that he showed, which varied by 0.5 degrees, and he was telling you how samskaras can be made to get that value closer to the ephemeris value. All that matters is what is the true longitude of Moon, what is the true longitude of Jupiter, Mars, Saturn, so on and so forth, to get to know at the time of birth or at the time of any activity what are the positions. We get it today from the ephemeris value, but then there is a traditional Indian value that has come, of which the Tamil part what that comes is from this text. A few minutes back is that, say you had that you have to get the ahargana, then you have to get the khanda, which means those vital numbers were important. What was 16,94,000 in the case of the Sanskrit text based ahargana, that is where it becomes 15,65,411 from the Tamil text, and that is where Professor Srinivas also commented that this is definitely before that 16,94,000 days ahargana. That is why this predates it. So, that is one number that is being fixed, which we get it from this verse that appears in this Cūḍāmaṇi Uڵḷamuḍaiyān, Yellaiyirinathin Mannan Veed Sūழ்குளம் எடுத்து பல்லியோனி கரித்து பலம் முதலாகும் சேடன் செல்விக்கேள் ஏரீர்மா, and so on and so forth it goes. So, the words here that are of importance which corresponds to numbers are again Mannan Veed Sūழ்குளம், which is your ahargana, Palli Yoni, which is that your 3031, and then Erirma, which is the 248, which appeared in those where you have to divide it by 1, 2, 3, 7, 2, then take the quotient, then you take the remainder again divided by 3031, then again get the remainder, then divide it by 248. So, this is a Tamil counterpart for it, but mind you, because it takes an ahargana which is before that, that is why we say this is earlier than that. As it was discussed, very in the same nutshell, that start with the number of days that has elapsed from the Kali Yuga, subtract 15,65,411 from that, then divide the residue by 3031, then again further divide the remainder by 248, and then the remainder obtained in the last division gives the serial number of the vākya among the 248 Pañcāṅgavākyas, which is to be used in the computation. That what just Dr. Pai concluded, that you had this Q1, Q2 and Q3, and then to that you add the value given by the vākya. So, here the similar thing is being done, but the Tamil vākyas are what are being referred to as. So, this is the text as it was also highlighted by Professor Srinivas, that it is predating and it is to the first text, even though Katapayadi was there from the 5th century onwards, and you had the Vararuchi Vakyas, but then this is the first text which uses the phrases and gives the Chandravakya-s, which was later seen in the other Vakya texts. So, the Chandravakya-s that you get to see, I mean this is a method that is being told here. So, these are the Tamil Chandravakya-s that we get to see, that is Vinnor Nadan, that is the first Vakya which corresponds in the Sanskrit counterpart. It was your Girna Shreyaha, which was 12 degree and 3 minutes. Here it becomes Vinnor Nadan. again it has to be reiterated that it is, as Professor Shri mentioned in the morning, it is not like writing the European maths merely in Sanskrit text, Sanskrit words. This comes after that Girna Shreya, but it is not the mere translation of that Girna Shreya, even though the Granthakara here says that he is referring to Parahitam, earlier Sanskrit text, and translating it in the Tamil for the local understanding. So what that exact text is, we do not know, but then it starts with again the 12 degree, 3 minutes, Vidnor Nathan, Paimbo Nindan, which is the second, whatever was earlier discussed. You get a lambda, and then you, for that, on that day when you are trying to calculate the true longitude of the moon, and then the first day is 12 degree 3 minutes, the second day is 24 degree 9 minutes, Girna Shreya, Dhenava Shri, like that you saw there. Similarly, you are seeing here Vinnor Nathan, Paimbo Nindan, Varai Pukoya, Titir Vengadam, so on and so forth. In one edition of this Cūḍāmaṇi Uڵḷamuḍaiyān, you see different wordings being used, like Vinnor Nathan in the earlier text becomes Vitto Nathan, Vaito Nitan, Vana Bhulokam, Vimi De Nargam. Like that, the vākyas changes, but the numbers that they decode remains the same. Now, because we have dabbled into this text, and now it is we are seriously pursuing it, what we also get to see is that this original work of Cūḍāmaṇi Uڵḷamuḍaiyān, if we look at it, it has been quite popular, and the tradition has been lived. It is not that it was forgotten. In the intermediate, it has also influenced other texts, like there is another text called Vaimīsvaram Uڵḷamuḍaiyān, and currently in the Tanjavur manuscript library, maximum number of manuscripts that they have on the astronomical treatises, in that the Cūḍāmaṇi Uڵḷamuḍaiyān's number of copies of manuscript happens to be more in that, which means it has attracted the people's attention for a long time in a wider way. Notwithstanding its popularity, the latest so-called critical edition that we have available for us is from the year 2007, published by the Tanjavur Manuscript Library. But there we see that there are lots of apparent mistakes, errors that have crept in, and especially when there are errors which are representing numbers and calculations, such errors are going to make a lot of differences in terms of understanding what the text is talking about, not merely pertaining to some linguistic error. For instance, like this, the vākya which gave us the Yerir Ma, Selvigel, it was actually Erir Ma, which corresponded to the number 248. Okay. But in this Satyabhama edition that of 2007 that's the latest, you see that the Erir Ma is wrongly written as Yeil Ma. Yeil Ma, then the coding becomes quite different. Instead of 248, which is Erir Ma, if it is Yeil Ma, the coding also would be different, because of which you will run into a lot of problems. So, to cut the long story short, there are several errors in the so-called critical edition as well, and it is our humble attempt now to come out with blemishless Chandravakya-s that are given in Tamil in these texts, and compare them that are available in different texts, and come out with relatively blemishless Chandravakya-s, and make a comparative analysis of how Dr. Pai had shown for 28th February 2025, using that method that is available in Sanskrit text, and see how the computation goes in this method. Those are parts of the ongoing series of work, of which this is the first work which is now under press in the Indian Journal of History of Science, and the other works are under progress, and pretty soon we will be out with them as and when they are ready.
Thank you.
Thank you very much.
So when you look at the Sanskrit statements, the entire statement denotes a number, whereas in the Tamil version you have to search for that number within that particular piece of verse. I mean, how does this work exactly?
No, there is no such thing. Sanskrit also, when it occurs in a verse, the numbers are in between. The rest of the verse goes on as it is. In Vakyas, it's only numbers. So when he is talking of Vinnor Nathan, that is just a number. but that's not just a number, that's a longitude. So Rashi, degree, minute, second, etc. But when these numbers are used to discuss an algorithm, it will come in the form of a verse. We didn't quote the Vakyakarana verses. Vakyakarana also has verses, and those verses will contain these numbers as phrases, and the rest of the verse will go on. That Nilakantha's Madhava's pi value, that first half Vibhuda Netra Gajayi Hutashana came, but then Navanikharva Mite Vritti Vistare and all that. So it's all part of a verse, and the numbers also come. Either whether it's Katapayadi or Bhūtasaṅkhyā, they are interspersed with the rest of the verse, both in Sanskrit and in Tamil. The Katapayadi can be used in most other Indian languages. There are in fact instances of its use in Telugu and Kannada, but it cannot be used in Tamil language. And Tamil was the home of vākya system, which was based upon things like Katapayadi. So there were Sanskrit books like Vakyakarana written, but before that they have written this Cūḍāmaṇi Uḷḷamuḍaiyān, and perhaps there are earlier works which we have to see.
Can I make one small comment? Yeah. See, the thing is, yeah.
Camera is.
Yeah. No, it is good, and it's, as I told earlier also, it is based on the Siddhantic expression for the Manda Samskara and so on. See, but we know that, the second correction to the moon comes. So, after doing all that, I think the whole Vakya system has to be reformulated, because if you want it very distinct, some kind of reformulation to suit on the average it may be okay, I don't know, that has to be this thing, but some kind of reformulation is necessary if, certainly the second correction is there and one cannot avoid it. One has to face this problem. Yeah.
No, it's very true. In fact, there is a work called Bijopanaya, which is attributed to Bhaskaracharya, because Bhaskaracharya's Siddhanta Shiromani does not have the second correction to the moon, what is called the evection, though it was known earlier to Munjala, who wrote in 932. He in fact formulated the evection correction in a form that was later on formulated only in 18th, 19th century. The first correction to moon came with Hipparchus. He had the eccentricity correction. Then Ptolemy gave the eccentricity plus evection correction. But Ptolemy gave a purely geometrical model, and if one took the geometrical model to be exact, moon would be moving, the distance of the earth to moon would be changing by a factor of 1:2 during 27 days, which does not happen. The angular diameter of the moon is around 32 minutes. It does not change to 16 minutes over 27 days. So it was faulty, but it was ignored. That fault was ignored. Munjala gave a purely analytical formula for the longitude in terms of sine, cosine functions and the sun's longitude. That was perfect evection correction, later on repeated by Shripati, later on repeated by in a different form in Yukti Bhasha and Nilakantha. But evection correction plus equation of center, when the distance between sun and the moon is 180 degrees or 360 degrees, will exactly become only this much. Meaning the simple formula for equation of center, or what is called the Manda Samskara, that is given from ancient times in Indian books till Munjala, that is exact as far as only the evection correction is concerned. It vanishes at when they are in opposition, when they are in conjunction. So they do not come into play in eclipse calculation, and for eclipse calculation this calculation is reasonably exact to the extent only two terms. That is that. So these astronomers were using this simple method to calculate eclipses only and showing that magic to the Europeans in the late 18th and early 19th century.
No, Vakya system was not used only for eclipses.
No, it was used, but
so eclipses they turn out to be correct, okay? But for other days also they were using it, so there is.
No, but unless you use evection, a usual table, there is no Vakya system, because you have to take into account one more.
It has to be somewhat reformulated.
Like the planetary version.
It has to be reformulated.
So use of Vakya for, as Professor Shri was pointing out, for the other 15 tithis, will be 1 or 2 degrees different
Probably, yeah.
from the actual value of the longitude of the moon. And that's why Bhaskara is supposed to have written that book called Bijopanaya, though he neglected the eviction correction, the second correction in Siddhanta Shiromani. But there are problems with that text also. We do not have a good edition of that text.
So maybe you can give the concluding remarks. You can give the concluding remarks.
Oh, yes, sir. Last question, let's say.
Sir,
Oh,
what is the exact meaning of vākya? Is it
Phrase.
formula or
phrase,
phrase only?
phrase.
So what is the speciality of vākya? Because we have 3 parts of Siddhanta: Siddhanta, Tantra and Karana. And what is the special in vākya? Is it comes under the Karana Grantha or Tantra Grantha?
No, Vakya will always be an approximate thing because Siddhanta is considered to be exact. Therefore, Vakya is more used in Karana Granthas.
Karana.
The Vakya Karnas is for Siddhanta Mahatantra.
He wanted to ask something. That be last question. Just one question.
In terms of practical considerations, while calculating eclipses. In terms of practical considerations, while calculating eclipses and all that, that is fine. But there is this problem of precession of the Earth's axis, because of which all our festivals are going off the season, are not synchronizing with the season. I mean, is there a way to reformulate these things so that they become more accurate?
Okay, this is a good question, but a different question. But India was the first country to formulate precision exactly. Surya Siddhanta has a value of 54 seconds for the precision of ayanas or equinoxes, whereas it was 1 degree per 100 years in the it's 1 degree per 100 years in the Hipparchus Ptolemy tradition, which went on till almost 15th century. And even the movement of the pole star, which is also similar to the precision of equinoxes, was known to the Indians from very ancient times. So this has all been taken care of in all our Pañcāṅga, except that in last 200-300 years, we have stopped looking at the sky, and we have stopped looking at the sun also seriously. So this Uttarayana and Dakshinayana, the day on which the sun exactly starts the southern movement and northern movement, which anybody can observe by daily observing where the sun rises, and the day of Vishuva, that is the day and night being equal and sun rising exactly at the east. These 3 days, because of precision of equinoxes, keep moving. The star associated with them will keep changing. So today we have all this confusion in our traditional Pañcāṅgas published in India, which print Uttarayana to be on January 14, which is called Makara Sankramana. So for sun entering into Makara Rashi is fixed by a certain number of stars. There is no ambiguity about that. I mean, except what is the exact 0 point of Meshadi, which there are some differences of opinion in the current 20th century. Otherwise, Makara Sankramana is January 14, but the Uttarayana is on December 21st. So this is a problem which we have put upon ourselves by only following books and not looking at sky, or by only listening to non-Indian sources and neither looking at the sky or looking at our ancient books. So this we should correct in our traditional Pañcāṅgas, that Vishuvat is on March 21st, around that time. The true Vishuvat can be different by a day, this way, that way. The true Makara Sankramana is always around January 14th, 15th, but the true Uttarayana is around December 20th or 22nd. If you go to older inscriptions, you see that this is being all followed correctly, the ayanas. But the current, and all Indian books will write what is known as Ayanamsha. And therefore there will be no confusion between the day of Uttarayana and the day of Makara Sankramana. They differ by this Ayanamsha, which is about 23 or 24 degrees today. So that's why from December 21st we are pushing it to, from January 14 we should push it back to December 21st. That is the meaning of the Ayanamsha. But we have stopped looking at our traditional texts also and the sky also. Therefore the traditional Pañcāṅgas have been following that. So they are not really traditional in that sense. All traditions which take old books alone as authority, but are a single book as authority or a single person as authority, will have problems unless you critically check them with the actual facts or actual observations. So then you have to look more books or do better observations or look for better commentaries of your tradition, then you will be able to keep the tradition alive.
Sir, just I am adding, we have a basic formula that any systematic procedure in Vedic text, we have Vaidika nam nakshatresu prasakti. It is theory. So when we are talking about Parva, Ainansha or formulating Pañcāṅga for our celestial work, we can adopt Sayan Paksha. But when we are calculating for our rituals and our dharma and parva, we should adopt nakshatra paddhati. And nakshatras are, we just nakshati nakshatram, it is, as Siddhanta says. So there are two series of Pañcāṅga, Sayan Pañcāṅga and Niran Pañcāṅga. We can calculate Sayan Pañcāṅga for by Dikram Sanskara for exact position, and to calculate our parva and dharma and tithis, we should follow Niran paddhati, and that also is a
That's
part
correct.
of
I think I am just stopping you because there is shortage of time. I have understood your point, but we are using only nakshatra paddhati only. Even tithis are by nakshatra paddhati only, and the nakshatras are also by nakshatra paddhati only. But the sun's ayana has to be fixed by the using the correct ayanamsha, and the daylight, the day on which day and night are equal, all those things. So all those phenomena which depend upon the position of the equinox and the position of the ayanas have to be done as per the actual ayana, because those ayanas and those visuals are changing by 1 degree in 72 years. And therefore, similarly the pole star, there was no pole star before 400 years. There was a pole star 5000 years ago which was called Āryabhaṭīya in India. Afterwards for 4000 years there was no pole star. So now what is called Alpha Ursa Minoris is or Polaris is a pole star only last 300 years. So our astronomers did not use the word Dhruva Tara. They only said Uttara Dhruva and Dakshina Dhruva, which meant a celestial, north celestial pole. There was no Tara sitting there. There was a Tara sitting there 5000 years ago. There is a Tara perhaps now. It will be exactly very close to the North Pole, around 2100. So all these are known in our traditional astronomy. There is no confusion. We have stopped, as I again said, correlating what is written in our books by looking at the sky. If we keep doing it, there will be no problem, and we should read all our books more seriously than we read them. Of course, we will have to update them. It's not that the lesson of all that is to keep correcting them. That the entire history of astronomy is that. I think we should stop with this. Thank you very much.